Firstly, we should realise that this graph is a displacement time graph for an athlete who is running along a horizontal straight track. The time interval is 8 seconds and the graph indicates the displacement S meters of the athlete relative to an origin O. We should notice that during the first 6 seconds, the athlete runs out to a displacement of 16 meters in the positive direction and then returns to O. At time t equals 6, we notice that the athlete has returned back to position O, but he continues past his initial starting point, and so the displacement becomes negative. He continues to run until he reaches a distance of 9 meters in this negative direction, and then returns once again to O. It is worth noting that we can use displacement time graphs to calculate velocity. We will take a look at this next before looking at the detail of this question. The small scale below the questions is an attempt to show the position of the athlete at key times. Before we consider the solution of this question, it is worthwhile recalling that on displacement time graph, it is the gradient which represents the velocity. Firstly, a straight line section represents a section of constant velocity, and this velocity is calculated as change in displacement over change in time as shown. It is worth noting that the gradient and hence the velocity can also be positive or negative, and that a flat spot on the graph indicates where v equals 0. Curved sections on the graph represent periods of variable velocity. Here, the change in displacement over the change in time can be used to calculate the average velocity over a time period as shown. And also, the instantaneous velocity is given by the gradient at a point. We will now consider the solution of the original question. In part A of the question, we are first asked to calculate the total distance travelled by the athlete. Note that during the first 4 seconds of the motion, the athlete moves a distance of 16 metres in the positive direction. Then, during the next 2 seconds, the athlete returns to his starting position and so covers another distance of 16 metres back to his original position. Then, between 6 and 7 seconds, the athlete continues moving in the negative direction, covering an additional distance of 9 metres. And during the times between 7 and 8 seconds, the athlete finally returns to his starting position, moving forward a distance again of 9 metres. And so the total distance covered is given by 16 plus 16 plus 9 plus 9, which is a total distance of 50 metres. We are also asked in part A of this question to calculate the average speed of the athlete over this 8-second period. Notice that the average speed is given by the total distance covered divided by the time taken, which in this case gives us a calculation of 50 metres divided by 8 seconds, which gives us an average speed of 6.25 metres per second. In part B of the question, we are asked to find the times where the athlete is instantaneously at rest. These are the points on the graph where the velocity is instantaneously 0 and are represented by the flat spots on the graph. And these are clearly at the times t equals 4 and t equals 7 seconds. In C part 1, we are asked to find the time interval where the velocity of the athlete is negative. This is the region on the graph where the gradient is negative, and this is clearly for the time interval from 4 to 7 seconds. It is worth noting that when t equals 4 and t equals 7, the velocity is 0, and so it is negative strictly between the value t equals 4 and t equals 7. In C part 2, we are asked to find the time interval where the velocity of the athlete is increasing whilst the speed of the athlete is decreasing. If the speed of the athlete is decreasing, this means that the speed must be approaching 0. And since the velocity is increasing, it must be that the velocity is approaching 0 from an initially negative value. And this requires the gradient of the graph to change as indicated. And looking closely at the graph, we can see that this occurs between the times t equals 6 and t equals 7 seconds.
We're going to have a look at this question using Geogebra, and to do this, because we're not given the equation for the athlete's movement, then what I've done is made up two sections. The first one goes up to there, up to x equals 6, and the second one goes from 6 to 8. But the idea is that it mimics the curve closely enough for us to have a look at what happens. Okay, so the first thing is to look at the total distance travelled, and that isn't simple to get from the graph because the graph is a graph of displacement. And that means that it's telling us the distance from a point, and when we're above the line here, then it's moving in one direction. Conventionally we would imagine it moving to the right, in the same way as the number line is positive to the right. But then when it gets to x equals 6, or t equals 6 I should say, then the movement is to the left. Now, in terms of displacement, that means that at this point, when t is 6, then the displacement is 0, so it's back where it started. When t is 8, it's back where it started. So, in order to find the distance, as it says in the answer, we have to think about the fact that it travels that the athlete travels 16 meters to get to the peak here, another 16 to get back to the start, and then 9 to get to the negative furthest distance, and then another 9 to get back. What we can do is look at the total distance. Essentially we can reflect the parts of the graph so that when the athlete is moving back towards the starting position, so between 4 and 6, then that becomes added on. And so if we move this slider A, which is actually time, then we can see the distance point moving along. Don't worry about that one moving up, I'll explain that in a second. And when we get to here, then we can see that it continues to increase, and we can see that that portion is a reflection of this portion. So this 16 meters where it drops down when we're thinking of displacement is now moving up. And you might want to look at the Geogebra app for this at a later date, which you can get from your teacher. Now, if we carry on from 6 seconds, then we can see that this represents a reflection of this portion. It shows that it's going up, the total distance is still going up, and then we can see that that final bit is the same shape as this one, and that's because that is an increasing distance, and so the graph doesn't need to be flipped. And that shows us that we have a total distance of 50 meters, as we'd already worked out, but you can sort of see it graphically there. Now for the next part, when we're thinking about when the athlete is at rest, well, as mentioned in the solution, the velocity is the gradient of the displacement, because velocity is the rate of change of displacement, so that's ds by dt in this situation, and so we can see that it's 0 at the beginning because the gradient there is 0, the gradient here is 0, and the gradient here is 0, and we can trace that out again by sliding the time across, and so we can see that the velocity increases up to about here on the modelling graph that I've used. About there is where the gradient is maximum, and then the velocity starts to fall again, reaching 0 at time is 4, and then it's increasingly negative. To here. Now at that point it starts to become less negative, so in terms of its size it's falling, and it goes through 0 again at t is 7 as we've already seen, and then increases up through to t is 8. So that's the velocity, and again that has a direction because it's a vector, and above the line it's positive, the velocity, so the movement is away from the starting point, then it's 0, and there's an increasing negative velocity, which means it's moving back towards the starting point, as we can see, because the displacement from the starting point is going from 16 down to 0, and then at this point it's going in the negative direction, so it's moving away from the starting point until we get to t is 7, and then the velocity goes through 0 to become positive, and so it moves back towards the starting point. So that's what the velocity looks like, and we can put graphs for that on to the screen now. So that's the full graph, so we can get rid of the little dots. And we can also look at the modulus of the velocity. So the modulus of the velocity gives us the speed. So if we look at the first section, then we can see that the negative portion has been reflected. And then we put the other bit on, and again the negative portion here has been reflected. So these are the absolute values of the velocity, which is the same as telling us the speed. And obviously in an exam you wouldn't have to write all this down, you may want to sketch it to help your thinking, but the key thing is that when we're considering in the final part where the velocity is negative, or then in part 2 the velocity increasing and the speed decreasing, then by thinking about the fact that the speed comes from reflecting the negative portions, so these portions here, or in other words using a modulus function, then we now can answer that part C very easily. So where is the velocity of the athlete negative? Well, that's this blue portion here, so that's between 4 and 7. And where is the velocity increasing but the speed decreasing? Well, we can see that the speed is decreasing between 6 and 7. It's also decreasing incidentally between around here, this maximum for the speed and the velocity, down to 0. But then the velocity is also decreasing. So where is the velocity increasing? Well, Well, the velocity is increasing from 0 up to this peak, but also from 6 to 7. So the place where both the velocity is increasing and the speed is decreasing is velocity increasing here, speed decreasing, so that's between 6 and 7 seconds.